All right, to finish up on gravitational field strength, let's look at a 2D example. Again, the theories and the methodologies with the 2D examples, no different than any of the 2D stuff we did in kinematics and dynamics. Again, we just got to be a little bit careful with vectors and all that fun stuff. So we want to find the net gravitational field strength at P produced by these two 50 kilogram masses. So this mass is 50 kilos, this mass is 50 kilos. So what we're saying is if we place a test mass at this point, what is the gravitational field strength it's going to experience because of these two masses? So again, if we know the direction of our force of gravity, what we can do is determine where the direction of the net gravitational field strength is going to be. Well, because of mass A here, it is going to pull a test mass towards it. So we're going to have this contribution because of FA. And at the same time, because of mass B, it will pull a test mass towards it along this line that joins their centers. So I'm going to sketch that line in here with my very, very faint baby blue pen. So along that line is where we are going to have that force B. What that is telling us is that the net gravitational force is going to be in the south of west direction. That also tells us the direction of our net gravitational field strength. But again, this is just to kind of help us assign directions. So since I only have things going left and down, I'm going to say left and down is positive. Now, the other thing, I should have done this in advance. Direction's going to be real funny to kind of have to say, you know, so many degrees down from left. So I'm going to kind of cheat in the problem a little bit. You know, that's the joy of being the teacher. We get that executive power. So I'm going to call this up direction north and that direction east, which means I'm calling west and south positive. I'm really only doing that just to make direction easier at the end. I am cheating a bit, but, you know, again, teacher power. So what we want to do is we want to find the contributions to the gravitational field strength from each of these masses. So let's do that. So we're going to find the magnitude of G for each mass. So first up here, for A, we're going to have the mass of A times G divided by that radius squared, or that distance squared, which is 15 meters. So we get our 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We have our 50 kilograms, and then we're dividing that by 15 meters. And as always, do not forget the square. So let's put that in the old calculator here. So what are we getting for this? We are going to get something like 1.4822 times 10 to the minus 11 newtons per kilogram. So we'll hold on to that one. We're not quite done with that yet. We will put that in our back pocket for the moment. So it's going to be the same procedure for the gravitational field strength because of mass B. Only thing we got to watch out for is we want this distance this time. But we know that this whole thing here forms a right triangle. So I know both of these sides are 15. So I know that this distance RB, it's just going to be 15 meters squared plus 15 meters squared. And then we're going to square root that. So that's going to give us our distance along that line. And that is going to give us about 21.213 meters. So now that we know the distance along this line here, now we can find the gravitational field strength because of B, or its magnitude anyways. So the gravitational field strength is going to be big G times the mass of B times that distance here we just found. So, writing out this 6.67 and all the units, a lot of work. As you can see, I'm kind of really struggling to write out my letters clearly. So I apologize about that in advance. And then we're going to divide that, by that 21.213 meters squared. So we got 6.67 to the minus 11, 50 kilos divided by that number squared is going to be about 7.4111. Well, it's basically 4.11111 repeating, times 10 to the minus 12 newtons per kilogram. Now, when we did the 1D stuff, this was pretty much all we had to do. Unfortunately, this is not quite the end, because we see that this force, or this gravitational field strength, is acting at an angle here. That means we have to break it up into x and y components, because we're going to go want the total gravitational field strength in the x direction, and we're also going to want the total gravitational field strength in the y direction. This is going to require us to break this into components, which means we're going to need that angle in here. But again, we notice that this side here and this side here are the same, and we have a right triangle. That's telling us that this angle here is 45 degrees. If you don't believe me, do your trig work. But we need to break this into components. So I just kind of want to sketch this vector. So this vector of the gravitational field strength, it's going to look a little something like, this here. So there's our vector. There is vector g of b. What we want is we want the x component of this. So we're going to want that g b of x. And we're also going to want that g b of y. And then, of course, we know that that angle in here, that's 45 degrees. Now, I have called west and south positive, so I don't have to worry about signs on these. These are both going to be positive. Well, this x component here, we have this GBY is my opposite side of the triangle. GBX is going to be my adjacent. So to get the x component of this vector, I'm going to have to use cosine times my GB times this cos of our angle. Now again, the reason that this problem likely has everything at 45 degrees is because cos of 45 is equal to sine of 45. So if you mix up cosine and sine, you won't actually get the wrong answer. You'll be very lucky if you make a mistake in that case. So I'm going to get that the magnitude of this is about 5.240 times 10 to the minus 12 newtons per kilogram. And it's going to be the exact same thing for the y component, because we're just doing GB times sine of the angle, which is still going to give us the same number. But for me, I'm real pedantic. I like to write stuff out. Same with the units. As you've noticed, I'm very cautious to write out all my units everywhere. I know a lot of students are very lazy and don't like doing that. I very much do not like that habit. It's something that you should not do. But, I could go blue in the face lecturing you on that. Alright, so we determined earlier that the magnitude of this vector along this path is about 7.41 times 10 to the minus 12 newtons per kilogram. But to help us find the net gravitational field strength, we want to have that gravitational field strength in the x direction and the y direction. So we have our components of this vector. This vector only acts in the x direction. So what we can now do with these components and the magnitude of GA, this is now going to allow us to find the resultant. We're going to find the total x and y components. So we are going to find the total x and y components of these vectors. So for gx, my contribution to gx is going to be GA, because it's only in the x direction, as we can see here, plus the contribution from the x component of GB. So we're just going to write all this out here with all my lovely little extra sig digs. And I'm probably going to run out of space here momentarily, so I'm going to have to really try and conserve space as best I can. But anyways, I get about 2.006 times 10 to the minus 11 newtons per kilogram. So this is my total x component. And then my y component is just going to be the y component of GB, because we don't have any y component from the A mass here. It's only in the x direction. So my y component of this is going to be this 5.240 times 10 to the minus 12 newtons per kilogram. So at this point, I have everything that I need. I have my total x vector, I have my total y vector, so I can sketch my final little vector diagram here. So we said that positive goes west, so for my x vector I have this nice positive piece here going west. And then for my y vector, I'm going to have this piece going down since we called south positive. And then my resultant is going to act along this line here. So this line is going to give me my net gravitational field strength. Let me put that angle in there for good measure. So the last thing, and it's the same procedure we've been doing since kinematics. We have a right triangle. We want to find the magnitude of our net force. So we're going to use Pythagorean theorem. And then to find the angle, we're going to use a trig function. I think I'll probably use tangent, as I always do. So let's try and cram that in this little space. So this is going to be a test. Can I write my writing clearly but smallly? We shall see. So the magnitude of G is going to be this x component squared plus this y component squared. All right, here is the real test for this, and I think I'm already failing it to write. So let's see, 2.006 times 10 to the minus 12 Newton per kilogram squared plus, oh, it's going to be tight. And then we get that 5.240 times 10 to the minus 12 newtons per kilogram squared. Now we got to square root this. Oh, okay, I just crammed that in there. Right, so let's find this. So we are going to get about 2.07 times 10 to the minus 11 newtons per kilogram. So that covers me for the magnitude of G. It's quite small, but again, we're dealing with 50 kilogram masses. They're not going to produce large gravitational fields. We need really large masses to do that. So the angle, I'm going to use the gy and gx values. So this is going to require me to use the inverse tangent. So I'm going to take gy over gx, which is going to be the inverse tangent of 5.240 times 10 to the minus 12 newtons per kilo. And then we have this 2.006 times 10 to the minus 11 newtons per kilo. Alright, and what do we got going here? So let's see. I want to again make sure I got all the appropriate digits here. So I'm going to get it's about 14.6 degrees, and what I've drawn here is south of west. So we did a lot of work, but we managed to get it all in there. So I have my gravitational field, net gravitational field strength magnitude of 2.07 times 10 to the minus 11 newtons per kilo. And then I have the angle, it's acting at an angle of 14.6 degrees south of west. So last thing I like to do, I like to put this all together. I don't really have any space down here, so I guess I'm just going to combine them up here. So we can say that the net gravitational field strength is, where is that, 2.07 times 10 to the minus 11 newtons per kilo. And then this is acting at an angle of 14.6 degrees south of west. A lot of work, but again, it's all the same process since we've done through kinematics. Make sure everything is broken up into components, get a total x and y component, find the resultant from that, use SOHCAHTOA to get your angle, bada bing, bada boom, done. Just take it slowly, be careful with directions.